Hi everyone, thank you to be there for my talk, Attacking Hypervisors, where we will be talking about VM Escape on VirtualBox. Quick word about me. Okay. I'm Corentin Bayet, I'm a security researcher and CTO at Reverse Tactics, and I'm mainly interested in low-level reverse engineering and exploits, so kernel, OS security, obviously hypervisors, and embedded software also. You may have seen my talk last year here at GreHack, where I did an introduction to VM Escape, where I introduced a lot of concepts of what is a VM Escape, what is a hypervisor security. I introduced a lot of concepts that I will not retell today, so it's better if you've seen this, but it's not mandatory. I will do a few reminders at the start. After this talk, earlier this year, we participated to Pontoon Vancouver in March. So Pontoon is a contest organized by ZDI, Zero Day Initiative, where you are rewarded for demonstrating zero-day exploits on popular targets that the ZDI decides. And on this contest, there is a virtualization category where there is multiple hypervisors, or VirtualBox, workstation, ESXi, and Hyper-V. And during the contest, the rules are quite simple. Your exploit need to demonstrate a virtual machine escape. So you start in the guest with administrator or root privileges. The guest can be Linux or Windows, whatever. And you must demonstrate code execution on the host. In our case, it is an updated Windows running VirtualBox. And after that, after your VM escape, you can chain it with a local elevation privilege. So by attacking the Windows kernel for a bonus price, but it's not part of the virtualization part. And small information about the configuration. So of course, virtual machines can have a great variety of configurations when you can change the hardware that is the emulated hardware that is exposed to the VM, and it has a very big impact on the attack surface. And there is no actual default configuration. So you can choose to enable things, expose some hardware, but it must represent something real life, like you could find in the real life. And you ask ZDI if the configuration is okay, and they will tell you yes or no. But you don't have a clear vision of what you can enable or what you can't. You just have to ask. And finally, about VirtualBox. VirtualBox, if you already use virtual machines, you might have used it because it's the most popular for the basic features of an hypervisor. It is open source. It is really easy to use. It is free to use. It works on most operating systems. So yeah, it's a great product. And it's maintained by Oracle. They do not do any profit on this, so it's really cool. And but on the other side, they don't have a team 100% dedicated for the VirtualBox security. So during this talk, I will do just a few reminders at the start of a few things I need for the talk. And then my goal is to show how I did my vulnerability research on VirtualBox, targeting the Pontoon contest. So I already knew hypervisors before, but I never worked on a VirtualBox, even if I heard of it. Never worked actually on it. So I will demonstrate how I did my research from zero to an exploit, so with exploit development, and I will conclude at the end. So a few reminders quickly. So an hypervisor is a software that can manage one or multiple virtual machines on a single physical computer. In our case, the hypervisor is VirtualBox. We have the host, which is the operating system running the hypervisor. In our case, it's Windows, an up-to-date Windows. The guest is the operating system running in the virtual machine, so you can have multiple guests. In our case, we just have one. It can be Linux or Windows, and it is the attacker in the scenario. And I want to introduce two small concepts I will use a lot in this presentation. The first one is a GPA, or guest physical address, which is an address in the memory of the guest, where the guest thinks it's physical memory, so he thinks it's actual RAM, but it's not because it's virtualized. But it's the main way to communicate with the host, because when you talk to hardware or hypervisor, you use physical memory. So it represents an address in the physical memory view of the guest. And the second thing I want to introduce is power virtualization, which is a virtualization technique where you modify the guest OS, you add drivers, you add specific components to the guest to directly communicate with the hypervisor. So instead of emulating a real hardware, you just use specific interfaces for virtualization. And it is done to improve performance, usually, or to add features to the VM, like shared folders or anything like that. So yeah, two small concepts. And finally, I want to speak a bit about the communication channel between the guest and the host. So the guest, when he talks to a hypervisor, he actually thinks he's talking to hardware. So this is the same mechanism. So you use access to read-write access to physical memory. With the guest thinks this is DMA, so direct memory access. So you write into specific physical memory ranges to have a shared memory with the host. And then you can trigger specific actions like the hardware with PMIO and MMIO. So PMIO is port mapped input-output. So you trigger those by using privileged instruction. In x86, it's in and out. You might have seen before. And for MMIO, you just write in specific ranges, physical memory ranges that are reserved for the MMIO. And finally, there's the last part, which has hypercodes, which is specific to hypervisors for the para-virtualized device, so the thing I just talked about before. So yeah, so let's start about the vulnerability research. For me, the first step in the vulnerability research is to have a setup. You need to be able to debug everything you need, and of course, it might seem complicated for an hypervisor, but actually it's quite not. VirtualBox, the most code is in the userland process, so you can just debug it with GDB or WinDBG. You can even compile it yourself, so you can add things if you want. So there's not much to say on this part. It's quite simple. The thing I want to talk about is, in my opinion, you need a way to quickly test things. Like you want to be able to quickly test, reach some code, some hypervisor code easily. So like, the question is, how do you easily communicate with the hypervisor from the guest? And as I just said, the communication channels go through MMIO, PMIO, DMI, hypercalls. So to do that, you need to be able to read and write into the physical memory of the guest, and you need to be able to execute privileged instructions. So to do that, you need ring zero privilege, and you are supposed to write kernel drivers. But of course, I don't want to write kernel drivers because it's written in low-level languages like C. You have to handle the whole memory allocation and everything. It's hell to compile for drivers, and it will be dependent of your operating system. It can even be dependent of your operating system version. So of course, I don't. Each time I want to test something, I don't want to have to compile the driver on everything. So instead, I'm using an open source framework called ChipSec. Which was originally designed for testing the security of hardware or system chips, like UEFI BIOS, SMM, whatever you want. And ChipSec already developed for Windows and Linux specific privileged drivers. It will expose privileged operation to the userland. So you can allocate, read, and write physical memory from the userland. You can execute privileged instruction, like hypercalls, PMIO. You can read and write on the PC device. So everything you need to actually talk to hardware or to an hypervisor. And it has a Python API, which makes it OS agnostic. You don't have to write code specific for an OS. So this is an example of a code snippet I use to actually trigger some code in the hypervisor. You can just initialize the ChipSec object. It will load the driver. And then you can just do this to allocate physical memory. You can write into physical memory. You can write into MMIO and read in physical memory. You can do everything you need. So this is quite simple, and it's what I do when I'm doing hypervisor security. I'm just using Python. I don't want to compile the driver each time. So this is the first step. The second step, the actual first step for me, is the state of the art when you're doing a research. This is a very important step that you can't neglect. You have to put time into it. The first goal of the state of the art is to find generic information on the target, so public documentation, how the source code is architecture, how is it organized, is it fuzzed? If is it fuzzed, how is it fuzzed? Because you don't want to look at the same surfaces, for example. And the second part is, of course, you want to focus on this related security work, and you want to study the previous vulnerabilities because it will give you a lot of information. It will give you what kind of attack surfaces are exposed, the most targeted one. You can have the exploit techniques that will tell you what kind of bugs are actually exploitable. You can extract what kind of bugs are present in the code base, which I call vulnerable patterns, because you might want to look to search these patterns. And you may even need to reproduce those bugs on vulnerable version to make sure you understand them correctly. So that's why I say you have to put time into it, because you might find bugs just like that. And during this phase, you should write a list of everything you need to check after, because it might give you ideas. So I was doing exactly that, my state of the art in the first days. And I was studying this bug exploited by a former colleague from Synactive, Major Tomsek, which he found on use for Proto in 2023, so last year. And it was uninitialized memory in the function pgm fizread. So the function pgmfizread is used a lot in the code base because it's basically the function responsible for reading the guest physical memory. So it will take a source, the source address is the GPA, the guest physical address, and it takes a buffer on the side, it will just memcopy from the guest memory to the host memory. So to do that, the function has to do two things. The first one, it has to split the access page by page because each guest physical range can be located at a different place in the host memory because it's not one-to-one. The physical memory is usually not contiguous. And the second thing is that you have to handle the MMIO accesses because one GPA range, one physical memory range, can be registered as a MMIO, so a specific memory range. So you just can't read memory there. You have to call the appropriate MMIO handler to handle this part. So this is exactly what this function does. So this is an excerpt of the pgmfizread function. I simplified it a lot. You can do it as a loop. So start that loop on each page. It will take the size of the current page based on the offset. It will check if the page is an MMIO handler or not, and if it is, it will call this function, pgmfizread handler, to call the appropriate MMIO handler that is supposed to fill this buffer. And then if everything goes well, no problem. And if it fails, the function will stop right there. It will try to memset the buffer so it's not uninitialized, and return immediately, so without going through the other pages that might be remaining. The issue there is that this memset is not using the correct size. CB is not the size remaining in the pvbuff buffer. It's actually the size of the current page. So if you call this function with 10, and you are supposed to read 10 pages, and an error happens on the first one, it will fill the buffer for the first page, but the 9 remaining pages will not be initialized. So this bug allows when you call it, when pgmfizread is called from the host with a GPA you control, which is very common in the code base, it will read the buffer, the return buffer will not be initialized completely. So this is the very common pattern to be able to trigger it, but you need to find a specific code that will read some data from the guest, triggering the bug and get uninitialized data, and then write it back to the guest so we can read it and get actually the uninitialized data. And Major Tomsek the last year actually did it. He found this pattern in a device, XHCI, which is a USB 3 emulation. And he found it, he exploited 4.2, and he had a leak. So the impact of this bug, you can leak uninitialized data memory from the host, so you can get some stack or heap pointers depending on where the buffer is, and you can defeat SLR. So this is the bug from Major Tomsek, not mine. And the patch was quite straightforward. They just changed the size here from CB to CB read to completely initialize the pvbuff buffer. Okay, this is a great bug, but this function might still be dangerous if the pvbuff buffer is not filled. So what is happening in the pgmfizread handler actually is the buffer properly initialized there. And pgmfizread handler, as I said before, it will take the GPA given. It is supposed to be a MMIO range, and depending on the guest physical address, it will call a specific handler. And there's a lot of different devices with a lot of different handlers, so they don't all do the same thing. But basically, they're supposed to read from the take the guest physical address, read some data, put it in the buffer, and return a success or not. And are they all doing that? Well, nope. There is, for example, this MMIO handler for the bus logic device. Bus logic is a disk hard disk technology that you can enable. And there is a MMIO handler just basically does nothing. It just returns a success. And there is even a macro preprocessor definition to make sure there is no warning because the arguments of the function are not used. So this handler does nothing and just return a success. So if you go back to the caller, this function will return a success and the pvbuff buffer is still not initialized. So this is a variant of the bug. We have the exact same pattern but triggered a different way. And the only thing we need to find is the MMIO handler that will return a success without fully initializing the buffer. And there's a tiny detail with the handler has to be declared with a specific flag because originally the MMIO handler is supposed to only read bytes size of 1, 2, or 4. But if you declare it with this flag, you can use any size. But this is exactly the case for the bus logic handler, so you can just use that. So I just have to enable the bus logic device, and I can trigger this bug and get some a leak, and can defeat SLR. I don't even have to find the exploit technique because it's the same as the Major Tomsek one. So just like that. So in the first few days, I found this bug just by doing my state of the art, and I already had a leak. So I need to find actual bug to exploit now. So my goal is to use the exact same technique, use my knowledge I acquired during my state of the art to find bugs, quick bugs, without going too deep in the code. Like, anyway, hypervisors have a huge code base, so you can't audit everything from top to bottom. So the goal is to just use some tools like grep, or I use grep, but you can use CodeQL if you want, if you need. And the goal is just to find interesting code just by grepping or finding some interesting pattern like you collected during your state of the art. And you have another list of things to look at deeper. So I did that, and it was not a great success on virtual code base. I spent too much time because I found a lot of things, but it was mostly false positives. Like the vulnerability was not actually reachable, or they were not exploitable, or only reachable in the weirdest configuration that I could not use for the contest. So I spent a lot of time triggering a lot of bugs that I couldn't actually use. I spent like 2 or 3 weeks on using this technique without finding anything exploitable. But by doing this, I still acquired a lot of knowledge on the code base, so I've seen what was fine, what wasn't, and what kind of attack surface were interesting. And I decided to just take an attack surface and look at it from top to bottom. And to do that, I decided to look at the Virtio device implementation. So Virtio is a specification for a para-virtualization interface, so a specific component for hypervisors to expose to guests, and where you can implement multiple devices. For example, VirtualBox implements a Virtio disk and a Virtio network card, but there is more devices you can implement with this specification. For example, QEMU-KVM has more devices. But so this implementation is, of course, public, so multiple hypervisors implemented it. Originally, it was for QEMU-KVM, but VirtualBox implemented it, and some other hypervisors too. And the good thing about this is that you can compare the implementation between the hypervisors. So, for example, you can compare the code with the QEMU-KVM one and find some weird thing, maybe. And the VirtualBox code actually felt a bit weird. Everywhere in the Virtio core code, there was this macroprocessor definition, vbuf on stack, and if it's enabled, the virtubuf buffer will be allocated on the stack, and if it's not, it will be allocated on the heap. And I found, okay, this is weird code I've never seen before. I don't know why they do this. But what's even weirder is that in this specific part of the code, when this macro is true, it will allocate it in the heap using this function. If it's not, it will also allocate it in the heap. So, okay, this is really weird. I want to look at that. And that actually is the implementation of the Virtio queues. Virtio queues is a part of the Virtio specification in the core. So it is in the core of Virtio, and all devices use this mechanism to send and receive data from the guest. The problematic you want to solve with this mechanism is you want to send a lot of data from the guest to the host, or host to guest, sorry. And you just cannot use a single contiguous buffer of physical memory, because the physical memory is not supposed to be contiguous. It's supposed to be split to be efficient with the virtual memory. So a very common way to do this is that you have a queue of segment descriptors, where a segment will have a physical address and a size, and it will represent a chunk of contiguous physical memory. And you'll have a chain of those descriptors to actually have a very big size where you can put your data. So it's a very common way to solve the sending and receiving data for hardware or for hypervisors. And in Virtio queue, the descriptor looks like this. So you have 0x10 bytes for a descriptor, 8 bytes for the guest physical address, 4 bytes for the size, and some flags. And the important flags, there is 2 important flags. You have the next flag. If the next flag is set, it means the descriptor chain is not over. You have to look at another descriptor after that. And the other descriptor is located at the index, located in the last 2 bytes of the descriptor. So this is the index of the next descriptor in the queue. And the right flag is, if it's set, the buffer is supposed to be used for writing. And if it's not set, it's supposed to be used for reading. And that's it. So a chain looks like this. You have a first descriptor. The white flag is set, so it's supposed to be write buffer. The next flag is set, so there is another descriptor after that. This descriptor, the index is to 1, so the next descriptor, sorry, is at index 1. And you can do this indefinitely until you find a descriptor where the next descriptor is not set. So, of course, the hypervisor have to implement the parsing of this chain. This is what is done in this function. I will not say its name because it's complicated, but yeah. And this function is responsible for parsing a descriptor chain, as I just showed. And it's supposed to put the result of this parsing in the virtubuf object. The virtue_buff object is there's a lot of things in it, but what's interesting in it is the two lists of buffer. So there is two lists of a fixed size, 1024, one for the in buffer, for the reading buffer, and one for the out buffer. And each buffer is represented by a physical address, on a size both on 8 bytes. So in input it takes a descriptor chain, and in output it is this. So this function is quite straightforward. There is a single loop. In this loop, at each run, it will read a descriptor from the guest. If the white flag is set, it will put it in the in list. If the white flag is not set, it will put it in the out list. It will copy the GPA and the size into the table. And it will do this until it finds a descriptor where the next flag is not set. So with schematics, it looks like this. You have a descriptor chain. The white flag is set, so it puts it in the in list. The next flag is set, so it goes to the next descriptor. Then the white flag is not set, so it puts it in the out list, and so on and so on and so on, until it finds the descriptor where the next flag is not set. Quite straightforward. So of course, there is error condition to not to avoid going too far in the descriptor if you don't have enough place on the host. So this is a single error condition of the loop, and it is just calculating the number of in segments and out segments that were used yet, and check if it's bigger than the actual queue size. The issue there is that the queue size is not fixed. By default, it's to 1024, like the list we saw before. But it can actually be changed. It's controllable by the guest. You just have to write in the MMIO, and you can change this value to any value in 16 bits. So the actual maximum value for the EQ size is 0xFFFF. So if you go back to our descriptor chain, the list outside is still fixed to 1024, but you can have up to 0xFFFF descriptor in the chain. So you can just chain more than 1024 descriptors, and it will start writing the result outside of the buffer. So the host fails to properly check if there are too many descriptors in the chain. You can write up to 0xFFFF segments in a list of only 1024. And the result is you have an out-of-band write after the virtue_buff structure, which is passed in parameter. So let's see how we can exploit that. So the virtue_buff structure, as we've seen before, it can be located both on the stack or in the heap. So globally, the Varteo disk device will allocate it on the heap, while the Varteo network card will place it on the stack. So I can choose what device I want to attack, to choose what kind of exploitation I will do. I decided to go with a network card because to me, a stack buffer overflow seems way easier to exploit. And the vulnerability have a small detail, so yeah, you can write chunks of 0x10 bytes in out of bound, so you'll always write a minimum 10 bytes, but you only control 0xCCs of them, so 12 of them instead of 16, because there's a conversion. The guest physical address is originally stored on 8 bytes, and the end is also stored in 8 bytes, but the size is originally 4 bytes and converted on 8 bytes. So the last 4 bytes are not controlled. It will always be padded with 0. So you don't control everything you write in out of bands. So in the exploit, you can trigger this vulnerability by this function, by attacking the stack frame of this function, which is the specific function in the network card implementation. We already have a leak because we defeated ISLR with the first bug I presented. And VirtualBox is compiled without stack canaries, so you can. It feels like an easy win. You just have to write the return value on the stack, and it's a 101 stack buffer overflow exploitation. Well, actually, no. This is a representation of the stack frame of the vulnerable function. You have our vulnerable buffer that will overflow the rest of the stack. And on the left here, the green boxes is the values I can fully control because it's aligned on the GPA part of the out-of-band element. But the elements on the right in yellow, I only control 32 bits out of 64. The rest is 0, so I cannot fully control the value. And as you can see, the safe pointer is always aligned on the right side. So I cannot fully control the return pointer and cannot exploit my stack buffer overflow simply like that. And unfortunately, all the values before the return pointer are just saved registered from the previous stack frame, and they are not used in any helpful way. So there is nothing to do before the return pointer. But we are lucky because just after the return pointer, there is some objects stored in the stack, which are actually arguments to the vulnerable function. They are called pdins and ptcc. And both objects are used during the function to do some dynamic calls. So you can, if you override them and fully control them thanks to the ISLR leak, you can have 2 arbitrary calls before the function returns. It's not that much arbitrary because on Windows, there is a control flow guard. It will prevent you to just jump on a web chain. But what you can do basically, you can call actual functions. We can't jump on gadgets. Sorry. So we have 2 arbitrary calls limited by CFG, but after we do those 2 arbitrary calls, the function can't return because we overwrote the pointer to control them. So if the function tries to return, it will just crash instantly. So we have a stack buffer overflow. We transform it into 2 arbitrary calls, but the function must never return. The strategy we used the first arbitrary call to trigger something else, another memory corruption. I can't go into details, but actually we can trigger an arbitrary write with the first call, so it's perfect. And we use the second arbitrary call to just jump on sleep. And the first argument is a pointer, so it's sleep with a very, very huge value, and will just sleep forever. So the function like that will never return, and we transform our stack buffer overflow into an arbitrary write. We can just use it one time because we can't re-trigger the bug because the thread is now sleeping forever. So we just have a single arbitrary write, and we have ISLR defeated. So ISLR defeated gives us arbitrary data at known location. It gives us the address of web gadgets, and specifically it gives us the address of the stack of a specific thread, the XHCI thread, which we leaked using the vulnerability. So we know where the thread of this thread is located. And looking back at this thread is actually a worker. It waits on a loop. And it's actually waiting on a semaphore, so it's waiting for an event forever. And the event is waiting for is to receive a command sent by the guest, which we can trigger at any moment. So we know where the stack frame is located, and we know it's waiting in this function. And so the strategies will use the arbitrary write to override the thread of the stack frame of another thread, specifically the XHCI thread. Sorry. And we'll target the stack frame of the function waiting on the semaphore, override the return pointer with a single arbitrary write, and trigger the wake up of the thread by sending a USB command. The thread will wake up, jump on arbitrary location, and we just have full control because we bypass CFGs like that, because CFG does not only control the dynamic calls, it does not control the saved pointers on the stack. So we can just jump on our web chain and go to shellcode and win like that. I have a small demo, not live, sorry. So this is VirtualBox 7.0.14, the version of March of this year. The exploit is written in Python, as I said, but it's compiled in one single binary for Ubuntu. You can see that it's quickly leaked some values, and we instantly have the shell and the calculator popping on the host. So we escaped the VM. Thank you. Yeah, it's time for a quick conclusion. So as I said, the exploits were fully written in Python. I didn't have to rewrite it because it was just stable. So why bother rewriting it in C? We changed it during the contest. We triggered the VM escape, and then we changed it with the Windows privilege escalation, targeting the Windows kernel. So it's a bonus prize, and we had a full win because we are picked first, and we had no collision, so our bugs were not known nor used before. And so we just switched this chain. We won $90,000 in March this year. So to conclude, it was really a fun project for me. I never worked on VirtualBox before, even if I knew a lot about hypervisors already. I did the VirtualBox work in a month in total. As I said, I spent a lot of time trying to trigger exploit some bugs that I couldn't. I still learned a lot on virtualization because the code is really easy to read, it's open source, and it's really cool, and I had time to improve my tooling. And yeah, VirtualBox is a great software as is, but also a great software to learn about VM escapes, to learn about hypervisor security. As I said, it's open source, it's really easy to read the code. There are still some bugs to find, I think, and yeah, if you find some and exploit them, you can have a nice bounty at Ubuntu. Thank you very much for listening.